So today we're going to be talking a little bit about the visible qualities of the image. How do we take pretty pictures? What do pretty pictures look like? And what are the specific qualities of that? What are the ways that we will discuss whether or not a picture looks good or looks bad? Here's the learning objectives. So what are the three visible parts of the X-ray image? And those visible things are its brightness, contrast, and noise. We'll define each one of those, and that's really what guides this lecture. We'll talk about each one of those to great extent. We'll describe the significance of optimum contrast. We've already talked about that some, but we'll talk about it a little bit more and additional measures for it. And this chapter is full of good information in that. We'll talk about the relationship between brightness and penetration, which we haven't necessarily defined yet, but we'll start to move in that direction. We'll explain the relationship between image contrast and penetration, beam penetration. And we'll define radiographic noise. We'll talk about ways to improve signal-to-noise ratio, and we'll define image artifacts. All of those things are kind of in this weird example picture on the side. I think this is like an X-ray of a mannequin, like a really old mannequin. And so we can see both areas of poor penetration, where the image is just white. We also see areas that are over-penetrated, like the areas of the mannequin's arms. And then we see these funny artifacts, things that we don't necessarily expect to see on the image, whatever these shapes are inside of the area of the head and the thorax. Yes. So in Hollywood, they have this thing called the rule of threes. Anytime you're writing a movie script and you want to introduce a new character, you try to mention their name 3 times and then you move on, right? There's kind of a beauty and a symmetry to things that come in threes, and so we talk a lot about triumvirates and stuff like that. But the 3 things that our textbook talks about as causing pretty pictures, right? When we look at our image and we say, this is why the picture looks good, they are the brightness, which are the overall whites and blacks on the image. And I'm going to refer to that smooth jazz sample of Superstar, right? Why? Because all that cover song was concerned with was the music itself. It was not playing lyrics or anything else. It was just the way that the music sounds, right? It's just the instruments. Image contrast is all of the grays, right? It's all of the funny things that could be misunderstood or are correct. We don't know. And so that's like Karen Carpenter's version of it. That is her singing the song. What is the song about? We don't really know. I'll call that image contrast. The final thing is noise, and that's anything that shouldn't be whatever color it appears to be. And so that's that Sonic Youth cover where there's these noisy things that are going on in the background. We can't really understand what he's saying anymore. Like the song is clearly not about the lyrics anymore. It's about something else, this weird noise. And so this image here on the right also displays those from an imaging point of view. We have the brightness, which is, again is this, this is an X-ray of a statue, right? Like a hollowed marble statue, or a cast perhaps. And the whites are like its hair, for example, or the blacks of its eyes. The image contrast is those differences, all those grays within the images, within the statue's face. And then the noise is actually the fact that what we're seeing in the statue's face is the hair on the back of its head, right? So that's noise. We wouldn't want to see hair on this thing's face. We're just trying to get an image of the whole thing. But since it's superimposed, it's causing this data where we don't necessarily want data. Brightness versus density is the first thing that our textbook talks about. And I do want to point out one thing as I'm talking about these different concepts. I'm going to use the word image contrast today. And as I'm talking about brightness, I'm just going to talk about brightness and density, right? Because in general, we don't talk about brightness as being anything other than what's happening on the image. But contrast, we've got 3 different places contrast can happen, right? It could be subject contrast, which is what is there in the remnant beam. It could be image contrast, which is what I'm talking about today, what's apparent there in the image. And then finally, it could be some kind of contrast agent that we've administered in order to enhance contrast. But for the purposes of brightness and density, we will just kind of compare and contrast these 2 terms. Now, the terms are kind of interchangeable, but they're also kind of opposites of each other. right? So we don't generally talk about darkness of an X-ray image, but that's what density means. It means how dark is the image. We don't talk about how light an image is, we talk about its brightness. So brightness, if an image is bright, like this image on the left, does that represent over-penetration or under-penetration? It is actually an under-penetration, right? The X-rays did not have sufficient energy to pass through whatever that white stuff is in the patient's lower lung and abdomen, right? So there was not enough penetration to darken the X-ray board. So that is under-penetrated. It resulted in this image being very bright. If it's under-penetrated, the image will be bright. If it's over-penetrated, the image will be very dark. So this image on the right, they fried the patient's hand on this image on the right, and we've got this over-darkening of the image receptor. Questions?
Is penetration strictly kVp?
Kinda. Penetration refers to how much energy do these photons have? Do they have sufficient energy to pass through the anatomy or not enough energy to pass through the anatomy? We largely tie that to kVp, right? And we'll definitely continue to unpack that as we go along. But the short answer is kinda. Yeah. So within the anatomy of interest, the pixels should be neither completely white nor completely pitch black. They should be somewhere in between. That somewhere in between is where the diagnosis can happen, right? But just be aware that there's two different ways to basically talk about the same thing. I might ask you, which of the following would result in the image with the most density, right? And that might be one of the answers to which of the following would result in the brightest image, right? And it's actually talking about two very different images, right? So I wanted to provide you all with this example here. Our textbook does a really good job of talking about image brightness, and if you look at it, it talks about brightness and density. I've said brightness versus density because I do think that they're opposed concepts, kind of opposite sides of the same coin. But one of the things he talks about on page 213, towards the bottom of the page, is he says, to achieve appropriate brightness or density, the energy of the photons has to be sufficient to penetrate through all of the anatomy, okay? And that's towards the bottom. And I don't think there's anything I would add to that. Contrast versus grayscale is where we're going to spend quite a bit of our time now. I've tried to boil this down and keep this slide pretty uncluttered, but I'm going to refer to your textbook quite a bit. So it defines radiographic contrast or image contrast, right, as the proportional difference, aka ratio, between the brightness of two adjacent details, right? Grayscale, which could also be called contrast scale, is the range of different densities or brightnesses within an image. One thing to stress is grayscale is the opposite of contrast. We will talk about them in opposite terms. For example, something that has a high contrast has a short grayscale. Something that has a low contrast has a long grayscale, right? So I really like in our textbook this discussion of grayscale. It's one of the reasons I went with this textbook versus others on page 215. And I'm just going to go ahead and read this out to you, or actually, rather than read it out, what I want you to do is turn to page 218 in the textbook and look at these two different pictures, because they're showing you on these images the way to think about contrast. And they're actually showing you the step wedge that we used to use to make contrast measurements, right? So this is a high contrast image, and this is a low contrast image contrast-wise, right? The subject contrast of these two pieces of anatomy are roughly the same, like the attenuation coefficients of these chests are the same. But the image contrast is different between these two images. And the question is, why? Well, if we look at this one on the right, what we have is a high contrast image. And you might wonder, well, why is that? Well, they've given us this scale up here at the top that shows us. We went from black to white in just 4 steps. We went from black to white in 4 steps. So I'm saying this is high contrast. It has a short grayscale, right? Over here, I'm calling this low contrast. It has a long grayscale. So we went from black to white in more like 7 steps. It took a lot more steps to get from black to white. Why? Because there's more gray. So it's low contrast. It's a long grayscale, right? So that's what I mean by they're opposites. If that's not helping to look at those pictures, another way to think about it is imagine we need to build a staircase that gets up to the imaginary second floor of this building. So I want to get up to the top of that area right there, right? Now I could build 2 different staircases. One staircase, the steps are only going to be 2 inches tall, right? They'll be just 2 inches tall. It would take you a long time to step up all of those steps and get up there, right? It would be a really long staircase. Versus, let's say each step is 2 feet tall, right? Where you almost have to like climb up it on your hands and knees. You're going to get up that staircase really fast, right? There's not going to be that many steps in it, like maybe only 4 steps in the staircase, right? But it's going to be really hard to get up those stairs, right? That's the difference between high contrast and low contrast. High contrast has the high steps. It's really hard to get up all these steps. Low contrast, the steps are nice and low, but it's going to take me a long time to get up there, okay? That's the way I generally think about contrast and grayscale. And again, I am talking about image contrast, which I want to differentiate from subject contrast. They are 2 very different things. So be aware of those distinctions. Okay, noise. Noise we can call undesirable input to the image that interferes with the visibility of anatomy or pathology of interest. So it is that Sonic Youth song where I can't even understand what's being said anymore. Why? Because there's a lot of noise in this song now, right? Same thing can happen with our images. In fact, the noise is already there even in a good picture, right? So this image on the far left is a noisy image. Specifically, the kind of noise that it has is quantum model, right? Quantum model is there in every image that we ever take, right? It's the just Compton scatter. It's the electronic static within the system, right? What we need is sufficient signal to override that noise. So in this case, we did not have enough mass to compensate for the noisy kind of staticky stuff that's happening on the picture. But we can clearly see the noise on the left has destroyed the contrast that we would like to see in the trabecula of the bone. That's that fine kind of webby pattern within the bone. You can kind of see it on the far right image. There's those lines inside the bone. We call those trabeculae. And they are the calcium deposits that form the bone matrix itself. They are, in one way, our instant measure of whether or not we've got sufficient contrast. Can I see the bony trabecula, right? Is this sufficient information to see what I need to see? The image on the left, definitely not. I cannot see that. It's obliterated that contrast the noise has. The image on the right, yes, it's very apparent. There was enough signal to override the noise. So what we're talking about is this signal to noise ratio. Now, a high signal to noise ratio means that there's a lot of signal, enough signal to override the noise. So don't be confused on that. If you see a question asking about low signal to noise ratio or a high SNR, it's saying signal good, noise bad, there's more signal than noise. So that's the ratio, is signal over noise. So signal is all that desirable info within the remnant beam. So the primary beam has passed through the patient's body. It's now incident on the image receptor. Anything that is good and right within that remnant beam, we will call the signal, right? Purely speaking, it's the song itself, right? It's just the song. The noise is all the random scatter, x-rays, model, electronic static, and Sonic Youth type stuff that's happening, right? The noise that interferes with us being able to discern what's happening in the patient's body. If you want to nerd out on this, page 217, table 13.1 has a really great list, and it's not actually exhaustive. I can think of 1 or 2 other forms of noise that are out there, but he lists every possible form of noise that he can think of, from quantum model, stuff within the imaging cassettes and the imaging systems themselves, scatter radiation, all focus radiation, aliasing artifacts that again happen during processing, electronic noise, algorithmic computer noise, which, Ms. Wilson, if you're curious where the histogram thing, it's in that algorithmic noise. There's a bug in the system that's causing this silhouetting artifact. And then exposure artifacts like grid lines and destructive superimposition of tissues. So he's done a pretty good job of listing out for us what are all the possible ways that noise can mess up our signal. Artifacts. So this is a subset of noise. So underneath the umbrella of noise, we also have artifacts, right? Artifacts are anything extraneous that show up on the image in obscure anatomy of interest, right? So sponges, hairpins, dentures, jewelry. I mean, it's almost too much to list. Pretty much anything in the anus that should not be in the anus, we will call an artifact, right? In fact, this very first x-ray ever taken clearly has an artifact in it, like smooth move, Rankin, right? So don't beat yourself up if there is an artifact. Just do your best to get them out of the way, right? Ask the right questions. And finally, if you are curious about more types of things that people have put inside of their rear ends, there's actually a lot of Amazon books about it. This one's only $7. I'm not endorsing it one way or the other. It looks like it's a spring and perhaps a bottle of Pepto-Bismol. Yeah.